have my water. We can all start. They set up the quiz so I could get my own shirt. So today, I want to say thank you very much for the invitation, for the chance to be here. It's really a whole world and a whole project that I had very little idea of that is happening, and it's really exciting to see what's going on. And I think I will try to convince you that it's also very opportune, and the chance to do something really special is tremendous. And for that, I think I was invited to kind of help you look at the landscape of climate modeling. So I will try to give you a bit of a view of what happens with climate modeling and maybe a sense of some of the choices you could make and the opportunities that you have for further collaboration. So this is about 20 or 25 minutes on climate modeling. And I think the first thing you have to understand is that not all climate models are the same. So we use the word climate model to mean many, many different things over time and different places. And the differences actually do matter. Some differences are a matter of quantity and other differences are a matter of quality. So the first climate models, and ones that we actually still use today to interpret more complex models, are very simple statistical relationships that describe the energy flows. Something you might think of fully aggregated Earth system energy balance models, where we look at the total energy flowing into the Earth and the total energy flowing out of the Earth. And many of you, when you had classes, you did this as a little exercise. You wrote down these little energy balance equations and you solved them. Turns out we use models which aren't that different. They might have two differential equations and they solve for the heat content of the upper ocean and the lower ocean, and they have statistical feedbacks, and they capture the global picture very well. So you can use these very simple models to get a real good idea of how the global system has behaved over the last 50, 100 years. And even in efforts like in the IPCC, they'll use these models as a way to explore the space of more complex models. So these are energy balance models. The Earth is aggregated as a whole, and they do a good job of showing you how the Earth behaves as a whole. You can couple them to carbon cycle models with an additional 4 equations. You get 4 carbon cycle reservoirs. We use that in an introductory class. So these are very useful models. They've existed for a long time, and they describe things at a very aggregated level. If you want to look in a disaggregated way, there's a long tradition of modeling which we might call EMICS. There are sort of Earth system models of intermediate complexity. You'll be familiar with those from PIC and Clymer and the UVic model in Victoria. They have simplified ocean dynamics. If you look at the University of Bern model, which might be 2 or 2.5 dimensional, so they get a bit of they try to simulate in a statistical, physical way the overturning of the ocean and how that affects the evolution of the climate as a whole. And they typically apply patterns to the spatial distribution of quantities to give you a sense of the spatial representation. So you can think of those as sort of spatially resolved EMIC, energy balance models. And if you look, one of the things that most of our existing climate models do, and what we seem to think, although we don't really know if this is true or not, is that the pattern of warming in the future looks kind of like the pattern of warming in the past. And so using something like an EMIC is very useful because you can look at how the mean change evolves in a very simple and a very quick way. And then you can impose patterns on it. That's what they do at the University of Bern. And you can take patterns from the reanalysis. And those patterns are likely to be more realistic than any other model that you could use because we really have no basis to think that the changes in patterns that we see from more complex models, even the most complex models that I'll talk about, are necessarily better than just extrapolating the pattern of change that we've seen in the past. So that's a very simple type of model that you can use, an EMIC with imposing fine scale patterns on it. So these follow here. This is unresolved energy balance models. Then you resolve and you get to an EMIC. And then about 50 years ago, in the early 1970s, people began exploring a particular type of energy balance model, radiative convective equilibrium, which couples the surface to the atmosphere. That was Manabe's model in 1967. And the idea was if you took that physics and you put it in a kind of stirring flow. So you used simplified dynamical equations, not too simplified, but simplified dynamical equations to simulate how the eddies formed in the high latitudes and stirred. And you kept that statistical coupling that we used in the energy balance models. That's our modern GCMs that people use in CMIP and IPCC. So they're also very simple in the sense that they use a statistical relationship to couple the vertical physics, goes back to the 1960s. And then they use a sort of quasi two-dimensional stirring of the flow in different layers to kind of mix around what that one-dimensional statistical coupling is doing. They give you a pseudo-spatial resolution of the flow, so it looks like, I'll show you some pictures, it looks like it's spatially resolved. And these are modern GCMs. They don't really include more physics in the vertical, but they do include the stirring of the mid-latitude eddies. And we couple them to the stirring in the oceans. They don't have eddies generally, but a kind of a planetary scale eddy field, which looks like the EMIX. So these models have existed for about 50 years. They've been elaborated on. People add different components. And these would be, what most people think about when they think of global climate models. In the last 5 or 10 years, we've been experimenting with actually vertically coupling the physics. So adding physics to represent the vertical dimension of the flow, which is missing in the other models that we talked about, which do it statistically. And this allows us to look at flows with local granularity, and it allows us to, for the very first time, to bring the tropics into the climate system. These models, which I'll show you what their approach to the tropics, and that's why it's a great white spot, is they actually relax to climatology. So what people know is parameterization. The goal of a parameterization and what it's designed to do is to relax to climatology. And all of the global models that we've used to date basically take the entire tropics and relax it to what we expect it to do on average, which you can imagine isn't really the best framework for looking at extremes, but they weren't designed to look locally. They were just designed to include local effects to see what happened globally. I can put that in pictures and you can kind of see what they would look like. The first one isn't really moving. It's an energy balance model, and it would go on very long time steps with spatial resolution imposed by climatology. This would be a CMIP-5 class model. That was actually one of our more advanced CMIP-5 models run at a little bit lower resolution here. But you can see it's dynamic. It has westerlies that evolve naturally. They kind of look a little bit like storms. You can run this at a bit higher resolution. The physics doesn't change of the model. The storms have more features in them. You can see the tropics here as this sort of bubbling stew of stuff that doesn't have a lot of coherence that kind of comes up. But of course, what's happening in the whole tropics between here and here in this model is the atmosphere is radiatively cooling. And then there's a statistical model that says warm up, warm up, warm up. And then it radiatively cools, 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 warm up, warm up, warm up. And it happens with a diurnal cycle a little bit. And so you see that more over land. But the tropics is really here a bit of a toy in this type of models, and the effort was to put the mid-latitudes there because we understood the storms here and we could computationally resolve them. These are the type of models here that we've been playing with lately. So on the on your far left, that's what we call a global storm resolving model. So people have run these down to 200 meters globally for short periods of time and several kilometers for decades. In the atmosphere, we're doing this now in the Earth system. So we have fully coupled ocean, atmosphere, carbon cycle, interactive ozone, aerosols. These now run at a kilometer scale, but not for very long, so order of months to a year, and maybe several kilometer scales for orders of years. And then here, this is where we're headed in the field is what we call global large eddy simulation. So I think by the end of the decade, we'll be able to run snapshots of months, weeks to months at a few hundred meters to look at, a warm climate and a cold climate for months. We can run at a kilometer scale for years to decades and multiple kilometer scales for multiple decades. So that's where that's the layout of the field. I want to say something because we come back to this thing about the tropics being the great, I think you said this white spot. And you really have to understand that. I think a lot of people in our field don't understand that. But this is the original paper that introduced the class of models that we work with today, global climate models. And it's from Smagorinsky. And he said, what they were dealing with at that time, 70 years ago or so,
small computers, smaller than my iPhone. He says, in constructing a dynamical model of the atmosphere, they wanted to understand the atmospheric general circulation. They said, we have a choice. He says, we can treat transient dynamics of the large-scale motions explicitly and to calculate their statistics, or we can treat them parametrically as a statistical theory. He said, obviously the second is more appealing because we're intellectuals. We think we should understand these things. So he goes, the latter course has a natural appeal following the successful application of kind of these bulk aerodynamic laws from von Karman and Prandtl. The application of large-scale cyclones and anticyclones has been, people are trying this, he says. So we'd like to kind of do two. And they said, and from time to time, attempts have been made, e.g. by Bearson and others. In fact, it is employed implicitly via Namias, who was at UCLA, in operational forecasts. So people have been trying to parameterize the eddies. More recently, there's a hint of some success. Phil Thompson, who went on to set up the scientific staff of NCAR, is referenced there. He said, but there's still incomplete understanding of the statistical dynamic of large-scale baroclinic transient motions. These are winter storms, large winter storms, these big swirling things we saw, up here. This one I haven't animated, but the big swirling things we saw up here. He said, we don't understand the statistics of that and how they maintain the circulation. And so he says, this leaves one as the painful alternative. So basically he says, we don't understand the statistics of these storms. If we want to model the general circulation, we have to resolve them. Now, you could say that was 70 years ago, and we understand them now. So let's go back to the simple models. But the reality is, of course, we don't understand them. They're complex, multi-scale, difficult problems. So everyone just says, let a computer do that part of the problem. It turns out in the ocean, when people talk about mesoscale ocean eddies, they're talking about the same eddies here, but no one was able to resolve them. At this time he could, so he said, let's do it, and we never looked back. But you see, these are the storms and the instabilities of the mid-latitudes. Those are the things that fuel the westerlies and help us understand the zonal mean circulation. And at that time, people living in the mid-latitudes realized that if you wanted to understand their westerlies, our westerlies, if you wanted to understand our storms, it wasn't enough just to statistically parameterize them. Now, if you move to the tropics, you couldn't, there was just no thought or hope, or it was just completely inconceivable to represent the storms of the tropics because they had a much smaller scale. But the new class of models that I'm talking about, that's the claim, is that we can use these very high resolution that we're capable of today to actually bring the storms and the instabilities and the flows of the tropics into our vision of the Earth system with some parity to the way we represent the storms of the extratropics, right? So if you think about that, in the old days, we had the extratropics. We thought they were important. We'd represent them explicitly. We make GCMs. Today, we can do the same for the tropics, and we can have the two circulations working at parity to see the full emerging picture from a physical basis of the Earth system. The ocean is going through the same thing. We just had a conference in Hamburg called Cello, and the great excitement in the ocean is the idea that you can actually see the storms of the ocean now at scale, the mesoscale eddies, and sometimes even the submesoscale eddies, which are really important for, if you look at biogeochemical transport off in the upwelling regions or along the equatorial flows, if you look at biogeochemistry. So there's a lot of excitement in the ocean that we can see the scales of motion there. And here's a picture of the sort of storms of the tropics. It turns out this is the summer in the extratropics. But what I wanted to show you here is this is kind of a spatially resolved representation of storm systems in an area that you might be familiar with, which is Germany, northern Germany on the far right, and then you moved on to the higher elevations towards the Alps on the left, and you see the vertical coherence of storm systems, and you'll see if you put them into motion how the coupling of the atmosphere happens physically and kinematically as part of the flow. And to represent things like this, you need spatial resolutions of 100 meters to a few kilometers, and you begin to see this transient dynamics explicitly. So you can really see how the surface is coupled to the atmosphere, how that heating in the atmosphere drives circulations, how the condensate is distributed, that influences radiation. And all of this happens through the kinematic coupling of the flow. It leads to cold pools that rush down and spread out, which interact with the land surface and cause new clouds to form, and so on. So this is, again, is that cross-section, but I've colored it a little differently above. And what you see is that the rain is in the blue and the clouds are in the white and the ice clouds are in the purple. And you see that cross-section and the richness of the circulations that are embedded in it. And below is a very modern statistical representation of it, as we use in our global climate model, where basically what we try to do is we don't try to simulate the flow. We just say, well, all of that stuff, just what it does on average is it heats things and it makes condensate. And so we kind of slap on, some heating and some condensate, and that couples the flow and it moves along. And it turns out that this bottom thing, it's kind of funny because in a real model, what happens is clouds make rain. So what happens is when you have a thunderstorm developing, air converges, it goes up, it makes a cloud, rain falls down. In a parameterization, it's the other way around, actually. The rain forms and then it leaves behind a cloud. So you see in these statistical models, you often have to do funny things, which makes it all the more miraculous that they actually kind of work. So if you want to understand the global picture, it turns out that these very simple, crude approaches actually they do okay for the global picture. If you look at our global models, they've done a very, very good job over the last 50 years of predicting how the globe will evolve as a whole. So what we've shown is it doesn't matter how you really treat the tropics, for the globe as a whole. It doesn't matter if you get the pattern of warming wrong in the East Pacific or you don't get the drying over the continent. For the globe as a whole, the regional errors don't matter a whole lot. But of course, if you care about the regions, then that's an issue. So here's an example of some simulations we're doing recently, just to give you a sense of how the flow organizes. They're just fun to look at. This is showing you how convection, these are these pulses, these gray things that are building up. You can look on the edges to see how kind of like that cross-section I showed before is interacting globally and how it's generating the climate. So you're seeing underneath it, you're seeing the climatology of precipitation. It's also a very funny thing about the history of climate modeling is climate is the average of weather, right? So if you take every day's weather and you average together, by definition, that's the climate. So you would think to create the climate, you need to compose it out of the weather. And that's what you're seeing here. You're seeing the climate emerge from the weather. For computational restrictions over the past 50 years, we had to do it the other way around. We had to presume that we could simulate the climate, and then we would figure out what the weather was for that climate. So we used kind of thermodynamic rules to say how the climate would change, and then we tried to figure out the weather. So we don't have to do that. You can let the climate emerge, and you see regions that you know and love, their climatology emerging out of the weather, and you get the full distribution of the weather from the very strong storms to the small gusts, and you see how that all evolves. So this is something that a lot of us are really, really very, very excited about these days, is because we can make another leap in evolution of climate models to look at things at a whole different scale. I want to give you a couple examples of some of the things, we're just starting this, and some of the things that we're learning. So the models I showed before, the simple models, we've been using them to understand questions like what happens to the Amazon if you deforest. So here's an example of a typical experiment, is that when you deforest, you replace forest by savanna, and what happens is you reduce evapotranspiration. And so the idea is there's a positive feedback that happens, is that when you reduce evapotranspiration, then you'll have less precipitation, and then you'll have more drying, and so on. And this has been explored in a whole bunch of studies using regional climate models, using the CMIP class models from that sort of third phase of model development. And what they show is it's a fairly nice relationship between how precipitation changes with evaporation. So we thought to do this with the kilometer scale models. And when you do that, you don't have the restriction from the boundary conditions that come from the parameterized models if you're using an RCM. And if you're using the parameterized models, you don't have the the problem where you kind of assume you know how convection behaves because it's thermodynamically coupled to the surface. So in convection parameterizations, you're trying to get the mean rainfall for the boundary conditions. And so you're coupling, you know, air doesn't go up and form rain. It just says, oh, it's warmer at the surface. Let's add some heating and some rain. So you're coupling thing, you're making a lot of assumptions about how you couple the flow to the surface. When we do that with a kilometer scale model, what we see is that the pattern of rainfall, we don't see drying everywhere, but we see parts of the Amazon are actually a lot wetter and parts are drier. And on average, the net rainfall is about the same. And so if you look at this dot, you get an out of sample point. I call this dark energy because there's all these scales of motion that we know are there, but we just pretend they're not, you know, and as dark energy in physics is there's a whole bunch of scales of things which must be there, but we don't know where they are. And here we know where they are, but we pretend that they don't exist. So when we include dark energy, we're kind of out of sample. And so this makes us think there's something we don't understand there. Maybe in the end, we'll find out that this one was wrong and these were right. But we're exploring new physics, and we have a lot of reason to think that this one makes more sense than these. But that's fun. That's new physics that we're learning. Another example of new physics is this is one of the big problems, maybe the central problem of climate modeling at the moment, is that the patterns are wrong that we get out of the models. And you can run models hundreds of times, thousands of times, and they're always wrong. And the poster child of this is 30 or 40 years of Eastern Pacific warming that you see here. And this is an example of our current generation of models, the pattern of warming. So this, you see the red and the big blue in the Eastern and Central Pacific and all along the ACC here. So this is all cooling for an average Earth that's warming. And what this is supposed to show down here without looking at it, and so you have to trust me, or you can go look at the papers, which are well, there's another paper that would be cited there. But if you run 100-member ensembles, use lots of different physics, all of the models get this pattern, don't get this pattern. It's just the pattern is out of sample. So running more models doesn't really help of this class. The very first time we ran the kilometer scale model, the very first time we ran it for 50 years to do transient warming, lo and behold, the pattern pops up. It's there. And so that's this example here. So that's very exciting for us. There's a paper now in review because it was something we tried hundreds of times before. It didn't work, and we run it once with this new class of models where we have the circulations involved, and there it is. That's exciting. There's two hypotheses for that. We know that ocean eddies, which are now in that model, respond differently to wind stress than parameterized eddies, so that's a long-standing thing. And we also know that the orographies resolve differently. So as the jets move poleward, they'll interact with resolved orography differently than change the wind stress. We don't know which one, if either is the explanation. Maybe we got lucky, but we got really, really, really lucky if it was luck. And here you see, this is what our, a high resolution Earth system model looks like of the past. This is what we're doing today. And this is observations. And this is just a kind of a cutout of the ocean eddies in the Southern Ocean. So you can kind of see the difference when you have eddies. Some things also happen which are kind of surprising, like the low cloud, small stratocumulus clouds, which are really important for setting the climate in the sense that they help vary spatially the amount of solar radiation which comes into the system. Stratocumulus, we've shown before that to resolve the circulation of stratocumulus, you need centimeter scales. I think on a numerical model, if you actually want to get the mixing at the top of a layer cloud, you need, we've shown, about 10 centimeters of resolution if you want to do that physically. Here we're showing that the vertical diffusion, if you can resolve the gradients, actually doesn't do as bad as we thought. So I won't pretend that this is great, but here what you show is our kilometer scale model. I think this is 5 or 10 kilometers, and this is just an albedo. Just look in the blues for a second here. And then if you look at the black, this is observations here. And then if you look at the solid line, that's IFS. That's sort of the most sophisticated weather forecast model that we have. It's been developed over decades to try to represent clouds like this and other things. So with parameterizations, that's this solid line here. That doesn't do very good there, but it does pretty good here in Peru. And this is just what happened out of the box in our model, the dashed line. So it does okay. You can find other regions where maybe it does worse here, but you can look through those things. So there's some good surprises. There's also some bad surprises. So for instance, in the trade cumulus regions, the puffy little clouds you find in the trades, they tend to, the kilometer scale models, which under-resolve those clouds, make far too many of these clouds. And so you have to do something about that. So it's not like you get everything for free, but you get some things that you didn't expect for free. And some of the things that you tried to get seem to have a different effect on the climate system. Some surprising too, just in terms of the circulation. This is a tropical circulation. This is precipitation here, and this is latitude. So this is the ITCZ, a very coarse resolution. It's right at the equator. As you go to finer resolution, it moves off the equator. But by the time you get to about 10 kilometers, it sort of is doing what it wants to do. I'm showing lots of different simulations in color as you go from coarse to fine resolution. But the surprise for us was actually something that we never thought. This is the storm tracks. And the storm tracks just migrate, the storms, these mid-latitude storms that Smagorinsky thought he would get right. They contain this whole cascade of instabilities on top of instabilities on top of instabilities. And the smaller scales seem to break the waves on the smaller scales seem to break differently than the larger scales. And the storm tracks move progressively poleward as you get to very fine resolution. So even for some of the things that the original models were designed to do, we're seeing added benefit from these other models. This is a complicated diagram, and the only thing I want you to know from this is we're looking at the climate sensitivity of these new class of models. And as I said before, the old models were pretty good for getting the global picture right, and we don't see any major changes here. So the climate sensitivity looks about the same. So we have no reason, based on these new models, to question the global picture. But again, like I said, the surprising thing about the way we did things in the past was the global picture was about right. The first time we hooked these up, we had some familiar problems. This is the 80th quantile of precipitation. Black is observed and blue is the model. And if you look at that, you say, well, it kind of looks like that. But this is pretty disturbing here, is that we really have a dearth of rain. What we found is that this is very sensitive to how you couple low wind speed regions in the tropics to the model. And we're making progress. That's the latest version of the model there in terms of representing the precipitation climatology. In these are with fixed sea surface temperatures. But these are problems we're working through. So it's a new class of models, and we're trying to see what, it's kind of like getting a Mustang and learning to ride it. So we're trying to figure that out. It's fun because we don't see things as a statistic. We see them as an entity. You see ocean eddies. You can measure ocean eddies with a boat. You can throw things in the water and take it out and compare it to the model. Here's an example of a cross-section underneath a satellite flight. And what you can see here is just many different cross-sections that we make. It'll jump to a new cross-section, to a new cross-section. And the top is the cloud from the model. The middle is the interpretation of the model in terms of the simulator of the satellite, and the bottom is the satellite. So because we're simulating explicitly things that we observe, it makes the comparison intuitive. It's really hard to compare a parameterization or a statistical model to an observation. You only can really compare the outcomes. And here you get to see the pieces, and so you can develop a fuller understanding. So that's an advantage. What's feasible? Sometimes people are concerned that because this takes a lot of computing power, but why else should we have computers if we aren't going to do things like this? So I find it a bit disturbing that people think we should get rid of computers, or we should just use them for Bitcoin, or we should use them for something like this. We can simulate on a high resolution CMIP6 model, the kind that we used in the past. We can take one GH200 node and we can simulate about 26 simulated years a day. So we could use that computer as 6,000 of these nodes, so we can run 6,000 of those models. We can run 2 of them on this thing. I mean, the current climate modeling is not a computing challenge. It's really old technology. Or we can use these models to kind of push the frontiers of what we can simulate globally. So the 2.5 kilometer Earth system model, we could get about a throughput of 10 years per day on 256 nodes. So if you calculate 256, what is that? That's 20 of these we could fit on the big computer, and we get 10 years a month. So if you give me 3 months, I can run the full Earth system model and give you 30 years. If you want to run for multi-centennial timescales, these sort of models are the wrong model. You should use the other models for multi-centennial. If you want to run for multi-millennial timescales, then the old models are actually the wrong one. You should use the mix, and that's what people do. So we're opening a new physics and a new frontier. I think by 2030, we'll be able to run at 150 meters for weeks, and then it'll probably end because the computers won't continue to get, we can have that discussion. The other thing is that in doing this, we've developed new ways to make the data available. So that what's really exciting is to make the data. It's such an immense amount of data. It's just an individual investigator didn't even know how to begin using it. And so the beauty of this is that in trying to figure out how to make the data analyzable by someone like me, we made it analyzable for everyone. So I'm going to say a word about AI. I think AI has a hugely important role to play in this, and in particularly AI-assisted workflows. So AI-assisted workflows deal like things with data compression. They help with the data-centric programming, how to lay out the data on the computer a lot. They're really great for including things in the model that don't fit in. They're great for expanding small ensembles, for looking at scenario exploration, and for enhancing in user experience. And the way I think about AI is like this: it's our coffee sign. We all know that what AI is really great for is doing stupid things faster with more energy, and that's a good thing. What does this mean for TropEcS? It says there's a new world of modeling emerging. It's emerging here in North Germany. The leaders in the field are in Bremerhaven, AVI, with IFS and FESAM, and Hamburg with the Max Planck Institute. Both of these efforts are being funneled through ECMWF in Bonn, which is running Destination Earth, and there's a chance to plug into that. And here I just took one example of a recent person who is entering this Bremen landscape, who's really been at the forefront of some of these things, and he's sitting right there. Different shirt. Good thing, old picture. So there's a real chance to plug into some of these efforts. So what I hope you learned is that not all the models are the same. Understanding the difference is useful. We've made a jump to a new type of models, and maybe this could be interesting for you. Thanks.